So I want to point out to everyone that, a lot of people have been doing these online seminars for the last year. And there have been a number of people talking about truss. And invariably in those discussions, in those seminars, people start saying things like, well, we got to ask the manufacturer. Let's go check with the manufacturer. That's what you got to do. So I got one. I brought a manufacturer with me today. Todd will be doing the heavy lifting today with this seminar, and you'll get to see him in a minute when I get out of the way, and he'll regale us with stories about truss.
All that's I have
all things
for
truss. Right. Yeah. If we could keep those microphones off, please. I'd appreciate it. And as I told Will and Sarah before we got on, I think we want to do a little contest, see if we can pull off a little contest here today. One of the things that you also hear in a truss seminar, in addition to, and probably more often than let's check with the manufacturer, you hear the words, it depends, or that depends, something to that effect. So, both Will and I are aware of it. I was thinking, if we make a little contest here, if people want to get into a pool and put a number next to your name in the chat, maybe we could figure, I don't know if there's a way to keep track. And I certainly don't want to have everybody keeping track of a couple of words rather than listening to the information Will's going to give us. But, I thought maybe we could have a little fun with it. So, and I will tell you that if you're going to use the chat for anything, whether to throw in a number of times, to get into the pool for how many times one of us or both of us say that depends, make sure that your chat is set up to talk to everyone, because if it's set up to talk to me or to an individual, we won't see it. So, well, it's 2:06. We should get started here. Let me get this stuff done. You've seen that. This is the public safety announcement. Again, which I find important. I think Andrew, you're being a little, that's a little. Hopefully not. But no, the behind the scenes mental health initiative. We've talked about it before. It's extremely important, and please take advantage of it. If you know somebody who would benefit from this, please give them that information. And last but not least, the ubiquitous ETCP certified announcement. Please, if you're going to want credit for this class, send me an email by Friday afternoon, please. I'll put my email address in the chat in case you don't have it. There we go. And so that brings me to the end of the class. Thank you very much, and we'll see you all next week. No, let me try that again. It gives me great pleasure to turn the tables on Will, because Will brings me out to do the Tomcat U every year, and we have great fun doing that, and we do it in person. But in fact, that's the last gig I did before the pandemic hit. I flew back from the West Coast on March 8th, and March 13th, it was done. We were shut down.
Yeah.
So that's the last time I've been on an airplane. I hope I remember how to do it. Anyway, I want to introduce Will Todd, the COO of Tomcat Truss. Been around for not longer than he's willing to admit, but he knows a thing or two about truss, and hopefully he will impart some of that to us. And please, as always, if you have questions, give it up. Let's hear about them. Will, you can go ahead and share your screen and get started anytime you'd like.
How's that? Does that work?
Yeah, it worked.
Excellent.
We're off to a good start.
There we go. I'm just looking at some of the comments in the in the chat already, and people are expecting us, or at least me, to say it depends a lot.
Well, there's one.
So hopefully we'll do better than some of those numbers are.
Yeah.
But, Bill, I appreciate you having me on. In this world we're in over the last, 10 months, I guess it has been a little bit interesting. I think all of us have probably done way more Zoom meetings than what we would have done at any other time in our life. So we'll see how that goes over the next, hopefully 6 months. We'll be able to get back in person again at some point, because contrary to popular belief, at least myself, I do miss going out and seeing people and seeing friends and catching up and having a drink at a bar. That was kind of nice to do at one point in time. But like Bill said, yeah, I'm a COO here at Tomcat here in Knoxville, Tennessee. I've been with Tomcat now for a little over 20 years. I joined in May of 2000. Prior to that, I was a touring rigger and electrician with Dizzy on Ice. Yes, I was an old Feld guy. So I did that right out of college. I toured with them for about 4 years until Tomcat called and said, "Hey, you want to move to Midland, Texas?" Which I did, and now we moved here to Knoxville in 2000, right at the beginning of 2013, and then I guess in 2015 we purchased James Thomas Engineering. So we moved them from their factory in place across on the other side of town, moved all those guys here and with us, and we've been maintaining both the Tomcat and the James Thomas line of products here at this facility. So what are we talking about here today? We're talking about truss. So basically, what truss is made for? What do we use truss in our industry? So of course, we're hanging truss over people's heads. We're supporting audio, lighting, scenic, all the fancy automation stuff that seems to be all the fad over the last few years. We're doing that. We're keeping it up in the air, and we're trying to do it as safely as we can. Some other examples out there in the world of truss, and is all kind of doing the same thing. They're supporting the load at a right angle. So parts and pieces of a truss, we have cords. These are typically the members that run the full length of the truss. So on a box truss, you're going to have 4 of them. They're typically not welded on the ends either. Sometimes they are, but in most cases they're not. We have our diagonal members, verticals, horizontals, internal diagonals, our connection plates, gusset plates on a spigoted truss, spigots, which is going to be in our world, it's the male and female connectors that connect the truss together. And we have the very important one, the panel points. So that's anywhere where a diagonal or vertical intersect with our truss cords. And we'll get into panel points in much more detail later on. Our industry in the big scheme of things in the entertainment is fairly young. I think most of our engineering load tables kind of started to be developed late 80s, early 90s. So when engineers started to look at this and how it works, they really didn't know how a truss as we call it today, they didn't really know how to look at it. So what most engineers, or some engineers that kind of built the entertainment engineering industry that we're in now, they had to find something to compare it to. So a lot of them picked an I-beam. So we had our top chords of a truss that was comparable to the top flange of an I-beam. Bottom chords, of course, comparable to the bottom flange. And then diagonals are going to be kind of comparable to a web of an I-beam. Then we throw in some goofy things. We throw in our horizontal members that tie the chords together, and then we have our panel points. That again we'll get into as we go. Some kind of definitions that we use a lot. Span. A lot of times this is confused. A lot of times people will say span and relate that to the actual length of the truss. That's not typically the case. What we're dealing with is the distance between support points is our span. So whether it's a dead hung system in in a ballroom somewhere or a touring system, we're wanting to talk about the distance between those support points. We have our compression member. So that's going to be a member when it's applied under load where the ends are trying to be squeezed together. Typically the top chords on a piece of truss when it's rigged traditionally. Opposite of that is tension. We're trying to pull those members apart. Shear force, a force applied perpendicular to a member. So when we're attaching a span set, we're attaching a pickup bar, we're applying load to a member of a piece of truss, we're applying shear force in that location. A ladder beam. So a ladder beam is really the first, when we're building truss, that's the very first thing we build. We'll build the ladders to the truss first. It's a top chord, bottom chord, usually some diagonals and verticals that tie everything together. A box truss is simply taking two of those ladder beam members, throwing them in a jig, and now we create a truss. We add in the horizontals, we add in the internal diagonals, we put the connections on it or gussets on the end, depending on the type. And now we've got a box truss. Triangle truss is a little bit weird. Essentially, we're taking a ladder and then we're building another ladder onto the side and creating that in a triangular shape, and then putting the end connections on that as well.
Hey, Will, just
Yeah.
briefly here, with ladder beam, I've heard a lot of people call it a flat truss. Is that an appropriate term to use or not?
Yeah, I would say that's appropriate.
Okay.
Some other, when you start getting into the nuts and bolts of an engineering report, you're going to hear engineers talk a lot about moment. Kind of the best example for that is on a ground support system where the sleeve block attaches to the tower. That sleeve block and tower is really having to resist a lot of moment because it's having to resist the deflection of the roof truss on the tower, and those sleeve blocks are really trying to resist the rotation of that deflection. You're going to see a bearing member. So again, back to ground support, we're going to be looking at like a head block roller beam type thing that's resisting a lot of bearing. Slenderness ratio, that's something that the engineers will deal with when we start getting into longer spans. So the longer the span we are, typically the deeper or wider the truss we need to be able to resist that slenderness ratio. So we've probably all seen ladders somewhere that are hung, but the distance is too far apart and that ladder starts to lay over. That's what you're seeing there as a bad slenderness ratio in that ladder. Bending, of course, we're all trying to resist bending of some type, shape, form, or whatever. We could load a truss theoretically to within the load table and still have localized bending if we're not applying the loads in the right areas. So we have to be careful where that is. Truss design in general, when the engineers are mapping it out in their model, the noding, when we look at noding, if we were to draw a straight line, a center line between the diagonals, the chords, and the verticals, we would want all of those intersections to be right in the middle of the chord. That almost never happens just because of the spacing, especially in light duty where you start seeing a lot of space between the diagonal and a vertical. So we have a lot of those loads are, and a lot of the load table loads are dependent on that bending of the chord between the diagonal and the vertical. Buckling is, of course, it comes from compression. We'll see a member buckle when it reaches its failure at compression. Misnoding we talked about, and then the heat affected zone. That's really, again, it's one of the more important parts of the truss. So the heat affected zone is an area around the weld that is changed by the welding process. So Tomcat uses either 6061 T6 or 6082 T6, depending on what we can get our hands on. And that's a heat tempered material. So when we apply the welding heat to it, there's about an inch to an inch and a half circumference around the weld that temper has now changed. And typically that it's changed and it doesn't help us. It makes the truss more brittle. So if anybody has had the misfortune to see a piece of broken truss, and we'll see some in some pictures here later on, but most of your truss failures will occur within that heat affected zone.
Hey, Will,
Yes, sir.
before you go away,
Mhm.
Michael has asked what the difference is between bending and deflection.
Well, bending and deflection is really, I guess it's kind of the same thing. Bending is what we're going to see when we apply loads to a truss, and you see actual members bending within the analysis of the truss or when the load is applied. Deflection would be when you assemble an entire span of truss together and you apply load. You're going to have some inherent deflection as the truss resists that load. The key thing is in deflection, when you remove that load, the truss goes back to its original shape. When we have bending failure, that the member will not go back to its original home, I guess.
Okay, great. Thank you, Michael. Does that do you?
Absolutely.
Excellent. So this is just kind of a diagram of a side of a weld, a very, kind of a very simple butt weld joint. You can see where the weld comes in. This would be our standard, what we call a fillet weld. So you can see where the heat affected zone affects kind of that whole joint area. And engineers, when they are looking at a piece of truss, they've got separate calculations for the heat affected zone that's different than the material of the truss. So this is really when we have a customer call in and say, hey, I need help either picking a standard truss or designing a custom piece of truss. These are really the main three questions that the sales staff will ask that customer. Of course, what's the capacity required? Are we supporting a lighting rig, a 60K lighting rig in the old days, a moving light lighting rig? Are we hanging a Volvo at a trade show? I mean, what are we doing here for our load capacity? The length of span, the type of truss we select or design will vary greatly between the length of span. So, we're not going to design a 20-foot piece of truss the same way that we have to design a 120-foot length span of truss. Application, of course, this is big. Is it indoor, outdoor? If it's outdoor, where are we doing it at? So we'll have to research the local building codes to see what the wind pressures are for that area. Indoors, if it's going in a big convention center that has big air handling units, we'll still need to put some type of a wind load on the structure. Are we putting banners on the truss? Are we doing, I think a lot of us have seen those outdoor, like the rock and roll marathons, where they'll build a light duty cube or a long cube of stuff, and they clad it on all four sides. So that has a big deal with the wind in those situations. What are our size restrictions? Do we have to go 100 feet in a ballroom with the 14-foot ceiling? That's gonna really define how we design that piece of truss, because you're not gonna want a 6-foot truss in that area when the room is only 14 foot tall. What kind of conditions is the load gonna be performing at? Are there gonna be acrobats on it? Is it a regular static load that most of the load tables are based off of? So as we dive into those questions, that really helps helps us narrow down or design what we need to design for that situation. We'll go through and we'll pick material. Of course, everybody is used to aluminum truss. So 9 times out of 10, we're going to be designing an aluminum piece of truss. But we will get into steel, especially in outdoor roof systems. A lot of the permanently installed roof systems that are outdoor, they're not going to want to have a bunch of external guy cables going out to anchor locations, forward, back, side of house, that kind of stuff. So we'll design foundations and steel towers to do the work of the guy cables, to be able to meet the local codes. We've done some work with plastics. We've done some work with carbon fiber. That kind of stuff is more exotic stuff. Tends to be more expensive. So in most cases that hurts us on a budget side, but we will get into that as needed. Once we select our materials, we'll start looking at what the members need to be, whether are we designing with our regular 2-inch 1/8 wall cords, or do we have to go to 3-inch quarter? Do we have to go to 2.5? It all kind of goes from there. Connections. Are we doing bolted connections, which is typically more user-friendly, or are we able to do like an inline axial spigot connection where we need more efficient load transfer, and some more durability as well?
Will, can I translate here for just a quick second?
Yeah, absolutely.
The inline axial, you're talking spigot, right?
Yeah, spigot or a fork end.
Right. Okay.
Or, if the European trusses, those are going to be the same as like your conical connectors as well.
Right. With the ones with the hand grenades, right?
Yes, absolutely. Or the footballs or whatever.
It depends on whether it's East or West Europe, I think.
Exactly. In materials, we're looking for strength and self-weight considerations. In the early days, the late 70s, coming out of Europe, or especially the UK, you were seeing a lot of steel trusses coming out doing tours. We quickly just found out that we don't want to be lugging around a bunch of steel truss, and we have this material, aluminum, that has a good self-weight to strength ratio. But aluminum does have some issues with durability. And those are all the kind of things that we need to balance. We've all seen the trusses that have been dragged across the floor, that the ends of the tubes are kind of scraped, and there may or may not be issues there. We're going to look at manufacturability, with the tools, the equipment, and the personnel that we have in our house. Can we work with it? Do we have that resource? Can we get it? Availability is a big thing. If a customer tells us that they need a piece of truss in 2 weeks and we select materials that have an 8-week lead time, we're not doing anybody a service. Environmental properties, this is very important, especially for locations, theme parks that are near water. So, your Disneys, your SeaWorlds, Universal Studios, those kind of things. We're going to look at hardware, the spigots themselves. We may do stainless steel on all that. It's more expensive, but it really does prolong the life of that product. We'll look at the thermal properties. We installed a roof system in Dallas back in, gosh, it was before my time. It was just barely. I think it was like 98. And it was a 46 by 43, one of our standard catalog roof systems. And we got a call from them a little while, I think it was into its second season, that there were cracks forming in the hinge block about 4 feet off the ground, give or take. We were like, that's really weird. So, at the time, material suppliers, our mills, didn't supply material certifications. We had to do our own checking of the material. So our guy that did that went through and checked the material, and everything had come out. It was all tested with what it was supposed to be for 606126. So since Midland and Dallas was only about a 5-hour drive, we sent a couple guys up to take a look at it, and sure enough, there were cracks in the hinge blocks, and they were real thin, but they were there in the material, in the cords of the truss. This is summer. It's in July, so it's hot. It's probably pretty humid in Dallas too, and the sprinklers come on in the afternoon. And where do the sprinklers hit? About 3 to 4 feet on all the towers. So the heating up of the material and the quench, the heating up of the material and the quench over time led to the material changing its properties and having some cracks form in the material. So we have to be mindful of that. That's something that is hard to foresee, but it's something that we try and deal with on installations. You know, and especially in cold weather installations too. If we have an outdoor system and it's going to be cold, we need to think about how the temperature swings are going to be for while that piece, that truss, that roof, whatever is up. Because what we found out, you know, over the last few years is aluminum is it doesn't like temperature swings. So it can be resistant to a high temperature and it can be resistant to a low temperature, but it doesn't like to go high to low within a short period of time. So if you have high temperature swings, we need to kind of be mindful of that and see what we need to do there. And then of course, cost is the biggest one, and it's one of the more difficult decisions that the sales guys or anybody here has with the customer, because you know a lot of times the customer doesn't want to tell us a budget, or they're being coy about it, which we understand. But that really is helpful for us, because if we come out and design this really cool truss, the next touring truss that we think is going to be the next touring truss of the next decade, you know, if it comes out to it's a $5,000 piece of truss, probably nobody's going to buy it unless the value is just so much more. But in most cases, people aren't going to buy it. So cost is something we have to be very sensitive of. So as we change overall member sizes, that kind of changes with as the truss gets bigger. So, you know, our normal truss, 12-inch, 20.5, 30 by 20.5 on both the Tomcat and the James Thomas side. Your cords are going to be 2 by 1/8. Your diagonal members are going to be 1 by 1/8. Again, all 6061 T6 or 6082, and our filler wire is all 4043. And that's across the board with everything, unless we get into a special situation that we have to increase the strength of our filler wire, and that'll be driven by the engineer. But as we get taller, we need to beef things up. So, you know, we may go to 2 by 3/16 like we do with our spigot. We may have to go to 2.5-inch cords. We may go to 3 by 1/4-inch cords as we get into our big extra heavy duty super megas, things like that. Cord sizes is driving that, diameters, wall thickness, connections. You know, once we start getting into a larger truss and we're really getting into you know, the bigger materials, you know, there's really no reason to stick with a plated piece of truss, because we lose so much in that connection. So we'll pretty much stick with the axials. Anybody still use cam locks? I hope not. I hope most of those have gone away. But
run away.
Exactly. We have some truss sitting in our building that has been sitting here for almost 10 months from a customer. That a bunch of it is still still has the cam lock style plates on the end of it. Okay. That's why internally we still call those cam plates and not plates or something like that. So it's just an old slang term that has stuck.
Will you have a picture of a cam lock, or should I go looking online?
I've got one that we
can get to it later. I just, you know. Okay.
Bolts we talked about, spigots we talked about. So our design philosophy when we're designing a piece of truss or a system is we always want to identify and eliminate the weakest link. A lot of times we're not able to do that, but we want to have the weakest link, something besides the truss. We want to have it to be the motor or the anchorage point that we're going into, things like that. We don't want to have a piece of 12-inch truss be the weakest link of the system. So what we'll do is we'll change stuff. We'll change the overall size of the truss. So if we have a 12 by 12 plated truss with bolts, a 40-foot span, uniformly distributed load, capacity of 840 pounds right out of the catalog. So 3/8 inch thick connection plates, 2 by 1/8 round tube cords and horizontals, and 1 by 1/8 diagonals. All we do now is go to a larger 20.5 inch piece of truss, medium duty, and look what that does to our loading. All exactly the same materials. All we've done is gotten bigger. We change our cords. This example is not as clean, but we have our 30 by 20.5 heavy duty truss with spigots on a 60-foot span. UDL is 4710. So now we're gonna go from a 2-inch by 3/16 round tube. We're gonna go to a 3 by 1/4 in our extra heavy duty. Yes, we do get a little taller as well, but we're almost 3 times as high on our load capacity over the same length of span. So changes in sizes, changing the materials really make a big deal, a big difference in the loading of the truss. Wall thickness. Do we think that that's going to make a difference just by changing the cord wall thickness? Anybody? You think so? 20.5 inch medium duty truss. We looked at this already. 1/8 inch wall, 2040. Studio truss. Everything's the same except we go to 3/16. We've got the same capacity. Now, why? Why is that? Why would we have 2 pieces of truss? One is considered an upgrade in studio truss and more expensive, but the capacity is the same. I know this works better when we're all sitting in a room together and we can yell at each other.
More durable?
Well, it maybe because it means that you can run a lighting C-clamp bolt a little deeper into the tube.
Yeah, it's a little bit more durable, and that's exactly why it has the name studio truss, is because we designed that for mainly use in studios where people were still using the C-clamps, digging holes in the truss. They were going through regular truss like crazy. So we developed studio truss. But the capacity thing's an interesting issue, because really that tells us from an analysis standpoint, the cords are not our weakest link. So there's something else in that truss that at least on paper is a weaker link.
Put all the pieces.
Hey, Will.
Yes.
I've got, and folks, could you turn off your mics if you're not talking? I've got a bunch of questions in the chat. Is this a good time to ask a few of them?
Yeah, absolutely.
All right. Well, Gordon was asking, you had mentioned at one point that bolted connections were easier. And I think Gordon would like to know why you think they're easier.
I don't think they're easier. I think from what we see here in the U.S. is that there's so much bolted truss, and it's more easy on the budget, because it is not as expensive as a spigoted piece of truss. But you see more of that here in the North American market than what you see in other areas. If I was building an inventory, personally, I wouldn't have a single piece of bolted truss in my inventory. It would all be spigot.
And why is that?
Well, you just get so much more performance out of it. In my mind, it is easier to install, to put together. You're driving a pin and not having to deal with wrenches and things like that. For me, it's a better product, an easier product to deal with.
Right. And I would agree with you. I also agree that because the bolted is so prevalent in this country, there are still a number of people who really don't know how to handle or deal with a spigoted connection.
Mm-hmm.
The number of times I've watched people try to drive a pin in from the wrong end. I was like, really, guys?
Yeah, there's a reason why on a Tomcat spigot that there's a countersink in there.
Yeah. Richard, I think I'm going to skip over your question. No, we'll do it anyway. Usually we reserve this for later, but our buddy Richard Crum has asked, wondering if it's true that Tomcat uses a safety factor of 1.2. Is it too early for that question? Well,
it's never too early for that question, because I know it's coming. The answer to that question is no. Tomcat does not use a safety factor of 1.2. That being said, That's not too far off from what the safety factors are in truss. There are at least 2 safety factors that the engineers use when they're looking at in a truss design. And those are driven not by the manufacturer and not by the engineers. Those are driven by the Aluminum Design Association. So they have their own code book, the Aluminum Design Manual, that tells the engineers how to calculate the capacity of aluminum. They have different safety factors based on yield strength, and then they have different safety factors based on ultimate strength, and they have different safety factors based on welded joints, welded connections. So if you were to take all the safety factors that they use put together, it probably averages out to about 1.7. And that is every engineer in the US that engineers to the design manual uses those same safety factors. And those safety factors, are fairly close to what we see in Europe with our German and European friends with Area 4 across the seas as well. So it's all within that kind of 1.65, 1.7 average.
Okay. Well, thank you, Richard, for attempting to throw Will under the bus on that one.
For a long time, everyone's always scared to talk about safety factors, right? Nobody wanted to tell what the safety factors were. And I get it. We, as a manufacturer, we want people not to think that they have an extra capacity on the piece of truss. Go by what the load tables say that you have printed in front of you. But in the big scheme of things, as we've become more educated as an industry, we as a manufacturer have had to kind of change the way we think about that too. So,
Okay.
Yeah, it's just different. It's a kind of a different way of thinking that we've kind of been toying with over the last probably 3 years on the way that we talk about safety factors, at least from the Tomcat James Thomas side.
Okay. I've got a bunch of questions. A lot of them are pretty cryptic, and I can't really tell if they're a question for you or a comment to the rest of the group. But I think, Jonathan, your question, are those against yield or braking strength? You are asking, if I understand you correctly, that the safety factor, you're asking, is it against yield strength or braking strength?
Correct.
It's both.
Okay.
Like I said, the yield will have its own safety factor, and the ultimate will have its safety factor. So there's 2 of them when you're looking in those calculations.
Okay. Yeah, I'm like I said, I'm not sure how much of this are questions. So if I don't ask your question, it's because I'm not sure who you're speaking to. But Matthew Thomas has a 1-word question. It says towers ? Matthew, do you want to expand on that a little bit?
Yeah, that was an answer to the why we use the larger diameter cords. I was guessing that was for tower truss for more of a compression. When I worked for a staging company, we used larger diameter truss for the towers we used for our big audio hanging rig. So
Okay.
I was guessing that the thicker diameter cord was for if you were using it for a tower capacity.
Yeah,
So
a lot of the towers.
that was my answer to that question.
There you go.
Thank you. Got it. What about that? Would you use a larger diameter, a thicker cord for a tower, Will?
We do, depending on the tower itself. So on the 12-inch side with Tomcat, we've got three different towers. We have a Mark I, a Mark II, and a Mark III. So a Mark I is kind of your standard light duty truss. We just add a diagonal. Diagonals are on a third face. A Mark II, the core thickness does go up to 3/16. And then a Mark III is really just a spigoted piece of 12-inch truss. The only difference is the connection hardware. Instead of the rounded off instead of the square clevis pin, you have a rounded off clevis pin so that the sleeve block can travel up the tower. But like on the KT7 roof system, we'll go up to a 2.5-inch cord on that to help with the axial loading, compression, and things like that. So yeah, he's right on with that.
Okay, cool. Why don't you go ahead? I think that I think I've brought up all of the questions. Somebody can yell at me if that's not true, but why don't you just forge ahead, Will?
All right. So this is just kind of expanding on connections, on how the changes with the loading. So this is another back to our clean comparison of how the connection makes a difference in the performance of a piece of truss. So we have the studio truss, which is the medium duty 3/16 cords, plated, 20/40 load capacity over 40 feet. So the only thing we're going to do now is we're going to take the end connections off, and we're going to put the spigots or forked ends in the ends of the piece of truss. And look at that, we go to 5,480 pounds UDL over everything else is exactly the same. The cords are 2 by 3/16. The diagonals are 1 by 1/8. Everything's consistent between the two pieces. Why is that? Why do we have such an impact on truss, on the connection? When an engineer looks at the connection, they're not necessarily looking at the size of the overall size of the truss. So on a piece of 12-inch piece of truss here, you see that on a bolted connection, our hole centers is 6.771. Whereas on a spigoted, if our spigots were in the ends of the cords, we're at a 10-inch ladder. So the engineers are really analyzing a piece of truss that's now 6.771 and 10. So it has a big difference in the way that their calculations work. Kind of putting that into some real time. If we have a plated connection here with two pieces coming together, we have a load that's coming down the cord. Well, now we get to the connection, that load has to go down the vertical, across the bolts, up the vertical, and then back into the cords to keep going to its support point to where it can release that load. On a forked or a spigoted truss, we don't have that bend in the load path. That load is just transferring right on through. So it's like a superhighway for load transfer. Does that make sense, everybody? Awesome.
Yeah.
Some additional design things that we'll always looking at. We talked about slenderness, the width of the truss, however many supports we have, diagonal size. Anything that is 30 inches or taller that's spigoted, we typically upgrade our diagonals to 1.5 inches. We get more compressive capacity out of that larger member. Size of verticals, size of horizontals, we try and keep those consistent. Size of internal diagonals. The internal diagonals are going to be the same as the diagonals in the ladder faces. The welding filler wire, like I mentioned before, all of our standard product is 40-43, and most of the stuff that we build custom is 40-43, but there are projects that we get on where we have to up the capacity of the filler wire. So we'll go to like a 50-55, or I'm sorry, a 55-56 or something like that to get some more capacity out of that weld. Surface coatings, going back to what we were talking about with that roof system that had the cracks in it, we should have powder coated that member to kind of help with that. If we have a piece of truss that's going to be going into the ultra blue, clear water, blue water at Disney, is going to be submerged, we're probably going to look at some type of a coating that is on that. What we have to be careful of, though, is that if we powder coat a piece of truss, or if an end user powder coats a piece of truss, make sure that you deal with a powder coater that's used to dealing with aluminum. Again, and this goes back to the temper. So another quick little story. We used to build speaker bumpers for these were some Meyer Sound speaker bumpers, and we were using a powder coater in Midland, Texas that was used to doing oil field downpipe that goes down the hole, and they would do miles of it. But we were having them powder coat these speaker bumpers. He didn't really know how heat affected aluminum. He didn't understand tempering. So we sent them 12 speaker bumpers to powder coat, At the end of the day, he powder coated them and he just threw them in the oven and left them there all night long. So no problem, I'll pull them out in the morning, everything will be fine. Well, in that time of 10, 12 hours, whatever it was, of those bumpers in that oven that was probably 450, 500 degrees, our speaker bumpers were warped by about a ½ inch from side to side once we got them back. So heat, again, heat is that's the thing we fight the most when we're building a piece of truss, is controlling heat in aluminum, because as soon as you apply heat to a joint, the materials really want to move on you. So make sure you have a powder coater that understands heat and understands what heat does to aluminum.
Will, Jack's asking MIG versus TIG.
Yeah, absolutely. We use both. MIG is metal inert gas, and that's the gun that has the spool of wire on it, and as soon as the welder pulls the trigger on the gun, it's feeding aluminum into the joint. We use that on all of our end plates, or anytime we get thicker than 3/8 of an inch. So, we're welding head blocks for a roof system, the end plates on a piece of truss, that's all done with MIG. TIG is tungsten inert gas. So that's a little bit different process. That's the process where you see the guy holding the gun and he's got the rod of aluminum. And when he pulls the trigger, in a lot of cases, he'll step on you'll see him in other industries where they step on a foot pedal, and then they start dipping the rod into the heat. So we use that on everything but the ends. But we don't use at Tomcat here, we don't use a foot pedal. We set all of our machines are all set to the same, and it's a pull trigger. And once those guys get going, they're rocking and rolling. They're not burying the heat with the pedal.
And you don't use any robots at Tomcat, do you?
No robots.
Okay.
Robots. James Thomas had a robot, but really all it was used for was building trade show bases. Robots for building the things like what we would have with truss. The head of the welding head wasn't able to access at the right angle all the weird, the back end of a diagonal trying to get in there with the robot wasn't able to happen. So we were still having to manually at that point we're still having to manually weld on a piece of truss after it got done in the robot. So it really didn't make, for as much money as it cost to buy it, it didn't make a whole lot of sense, because and in our industry we don't have that economy of scale to help pay off a piece of equipment like that.
Right. Thank you.
Anything else? No? All right. Rock and roll.
There were some questions back up a bit. Andrew was asking about strength of bolts plus couplers. Not sure where he's going with that. Andrew, you want to explain?
Yeah, they're like these inserts. Oh, geez, feedback. There's these inserts you put in the tubes of the truss that you'd use in addition to bolts, and I don't know if that would add any strength to the rating or not.
Sometimes we do. If we have an area where we know we're going to have a bolt going through something that we're bolting into the side, we will add in a tube member to help it so it doesn't crush the material that we're trying to bolt together.
Okay. You're off and running again.
Off and running. All right. So this question goes back to, again, the traditional old school Tomcat used from the late 90s, early 2000s. We would always tell people lift from the bottom and hang from the top. That was it was kind of beat into everybody from a usage perspective. So, and I think in the big scheme of things, at least from our perspective, we really want we want that truss being squeezed together. We want it in compression. In most cases, we don't want to be lifting from the top and hanging from the bottom and being able to trying to pull that truss apart. Again, that was old school Tomcat training. This one still applies. This one still applies today. We want to apply our loads at the panel point. We don't want to deal with bending, so we want to make sure that we're applying pickup bars, span sets, however, whatever we're connecting to the piece of truss. We want to get as close as we can to a panel point so that the loads are going right into diagonals, right into verticals, and not having to rely on just the cords to resist that load.
Okay, now hold. Oh, okay. You're going to answer the question about top hanging and bottom hanging. Fine. I didn't know you were whether you were going to continue on that.
Yeah.
Go for it.
And
Go for it.
Again, this is something within the last couple of years. As we've matured as an industry, we've gotten more proficient. We understand the engineering a lot more than what we did back in the beginnings. Yes, the truss can be hung from the top and loads can be applied from the bottom, but we still like to have kind of best practice kind of thing. We still like to have the truss being squeezed together. I know like in straight spans, it's a real pain in the butt to try and get a truss level, to sit level if you're trying to hang from the bottom or rig from the bottom and apply loads to the top. It's just not going to work. So yes, you can do that in situations where you need to do that.
Is there any reduction in capacity between the two, top or bottom?
Again, 5 years ago, we would have said yes, because we were scared to come off of our original statement of beating the truss into the ground. So I think there for a while, we were saying that there's a 25% reduction when you have to do that. But in the real scheme of things, no, there's not a reduction when you need to do that.
You heard it first, folks.
Yeah, I'm letting all the secrets go here today. Orientation. So that's really kind of a thing. What's the top of a piece of truss? Do I make V's or A's? And what is a V or an A? So what we're looking at when I say a V or an A is what's the shape of the diagonals between the verticals. So you'll see that in medium duty. You'll see that in pre-rig. You will not see that in a 12-inch piece of truss unless it's spigoted, because there's only one member between verticals. In most trusses, we'll end up making a V, but there are others that you make an A. So I guess it just comes down to what we want to make sure. Is that the diagonal pattern is consistent between the span. Is there a top to the truss? In some trusses there are, like in the 20.5-inch truss family, there are 1-inch members that are on the top. In the bottom of that truss, those members are all 2-inch. That way you can hang more lights or more stuff from the bottom of the piece of truss. But the important thing is we want to make sure that the diagonal pattern is consistent throughout the span.
Will, can I go back on this for just a second?
Yeah, absolutely.
First, you're calling them V's and A's, which I have heard, but I hear more commonly M's and W's.
Yeah, if you're incorporating the verticals into that, absolutely.
Right.
Yeah.
And for my purposes, it's when I'm trying to decide whether it's forgetting about whether there's a top or a bottom, if I don't have to worry about, putting the top on the top, if I don't have that criteria, then I look at the ends and what I'm going to do with the ends of that truss. And in one very specific case, I want to make sure that I have V's or W's where the diagonal is coming up into the corner at the top of the truss at the end. And the reason for that is when I hang a horizontal lifeline on a truss, I'm going to the end, the cords on the end, and up to the hoist, over through the other hoist, and then back down again. If I can put my round slings into that notch between the end plate and the diagonal, it's going to keep the round sling from sliding down the cord however many free inches or a foot or whatever that it has. So that's one of the things that I do look at.
Yeah,
you're going to tell me I should stop. You're going to tell me I should stop doing that, right?
No, not at all. I mean, it's
Okay,
all
good.
about the application. there are certain applications. If you know you're going to have a plot, you're going to be using the truss, and that you've got a lot more loads, it may be advantageous to flip that truss upside down. I say upside down to where it forms an A. That way you have more places on the top of the truss to apply your load. So it really just depends on how you're using it in that situation.
Okay, I heard that one. Joel has a question that I think is appropriate for here. What is considered the load, the hang points for the panel points? Joel, help me out here. I think the typing got away from you. Can you help me out with the question? Joel?
Yeah, sorry. For hanging, like, because for lights or other objects, you're not going to always end up at the panel points.
Yep.
I was wondering if, when you're talking about the load, if the load overall where the motor points are being hung from.
I would say, we're not as much worried about lights. Lights in the big scheme of things don't weigh that much. So I'm not worried about, if you have a coupler or a clamp or whatever you're using to attach, if that's kind of out there in the middle between a panel point, I'm not too concerned about that. But definitely your motor points. If you're rigging down to pick up a video wall, you're hanging a Volvo, that kind of thing, you want to make sure you're close to you're right at a panel point.
Yeah, like video wall bumpers, I guess.
Yeah. Yeah.
Thanks.
Yeah, absolutely. Triangle truss is kind of weird. How do we orientate triangle truss? So again, this comes down to a usage thing. I think when you look in most catalogs, we always show the truss in an apex up configuration, which I know drives riggers crazy, because how do you hang a triangle apex up and still make it work? The reality is that the triangle truss can be either apex up or apex down. Connections, if anybody really wants to go out there and carry around a torque wrench at every load in, when people ask us, we always tell them 80 foot-pounds of torque. A lot of times this is relevant in permanent installs. So if somebody's doing an install at a museum or something and they want to torque the bolts down, that's what we tell people to do, is 80 foot-pounds. Again, hopefully you don't have cam locks, you're not using them. But there is an adjustment, a tension screw within the cam lock itself. So if it has too little tension on it, the connection will be too easy and it'll be loose. If it has too much tension on it, you won't be able to get the full lock on the cam lock. Back to the fork, it's really simple. Put the pin in, put the R clip in, you're done. Really, really, really easy there. Now we get into some fun stuff. I think we're
Hey, Will, just to give you a time reference here, it's 3 o'clock here anyway.
Okay.
So we've got a half an hour left of the official time.
Gotcha. Well, this part right here I think is really the meat and potatoes of what I think most.
Can we go back to the bolts just for a minute? You knew I was going to bring this. I was going to do that, right?
Right.
So you're saying that you can torque a grade 8 bolt to 80 foot-pounds, and I agree with that. But I think it's important for people to understand why they should not go beyond 80 foot-pounds. You want to do that, or you want me to do it?
Either one of us is fine.
Okay. Well,
a grade 8 bolt is a really where that bolt was developed for was the construction industry. So they're putting together buildings or whatever, and they're cranking these bolts down, high torque. But the bolt itself is meant to kind of expand as it gets torqued down. So once that bolt gets torqued down now that bolt is where it's going to end up being at a high torque value. Us in the entertainment industry, we're not using that bolts in that type of situation. So we don't want to expand the bolt we don't want the threads to be modified when we're using that hardware, because nobody wants to be replacing bolts every time they use a piece of truss. So don't crank them down overly tight, because you will mess up those threads, because then that bolt is really doing what it was originally made for. Now, Bill, do you want to expand on that anymore? Or we?
Yeah, no, I think just briefly, and the chat is
Yeah.
picking up on this. This wasn't a problem until people started using impact drivers.
Right.
And you know, people will set those, and they do have, you get a good size impact wrench, and you will get to 150, 170, 180 foot-pounds, which is what does a grade 8 bolt in. You know, it's now been torqued to its proper setting for a permanent use.
Right.
So in addition to them being ungodly loud, you know, torque wrenches are a really bad idea on a load-in. So that's the quickie for me.
Cool.
Should Greg Sullivan's asking, should lock washers be used on bolts for temporary truss structures? Go ahead, Will.
I would say no. The reason I would say no on that is that lock washer will dig into the aluminum material, and you'll end up damaging the inside of that plate and doing more damage to the truss than the good that you're getting from the use of the lock washer.
Okay. Just let's go ahead and do the
I have a question.
Who's got a question? Go ahead.
It's Gord again. I try and teach that nuts and bolts are married for life. And it's a losing battle. Because if they're deformed, they should stay deformed together, right? Or am I crazy? Am I trying to, walk across water here? Teaching stagehands.
It's always helpful to know where the rocks are. If you've deformed a bolt, then the bolt isn't going to perform. If you've deformed it, then you're not going to get a nut on it, I would think. And it is certainly time for the recycling bin. Yeah, I mean, I would, if you've got a bad bolt and you've got a nut that's associated with that bolt, I mean, they're still connected, then yeah, they both go in the recycling bin.
I think it is good practice. I mean, it is probably like herding cats, but to put the nut and the washers back together after you're done using them.
Yeah, they go right back together again. Somebody asked how many times can bolt sets be reused? We really don't know the answer to that question, because the bolt sets either get lost or stolen before we get to a particular number that we're trying to reach.
And that varies on how if somebody's banging these bolts together with an impact wrench on a venue, they may end up doing damage to the cam plate that affects the bolt threads, that bolt may not go back together after just one use. So it really comes down to how gently or how the product is being used as well.
And Bill, you're keeping serial numbers on all of your bolts and nuts and tracking their use, of course, for lifting applications.
Yeah, of course. You want to buy a bridge? Yeah, no, there are no serial numbers. Just to be clear, there are no serial numbers on bolts and hex nuts. At least none of mine have serial numbers.
Right. You're not laser engraving barcodes into the top of your bolts?
No. Got a little blood on them, but that's about it, I suspect.
All right, shall we continue?
Yes, please.
All right, so how do we attach to a piece of truss? So, I know just from my time in the industry and my time using the product before I worked for a manufacturer, I've seen some extremely creative use of span sets on truss. Most of that has to deal with trusses that are out of balance. Probably if more of the load is on one side of the truss or the other, riggers will take an extra wrap, they'll add a shackle, they'll do all sorts of stuff to try and adjust the truss so that when you lift it up, the truss still sits somewhat level. I think, golly, from our perspective, from manufacturer's perspective, what we really want to make sure that we're doing is, again, we're wanting to make sure that we're attaching the span sets or the pickup bar at a panel point as close to it as we can. And we want to make sure that we have members that are resisting the forces against where the span sets are attaching to the truss. So in like the double pre-rig example, which is the first one there on the left, we choke around the bottom of the bottom cord and we come up around the outside cords. So on the top. So on the top, we want to make sure that we're somewhere where there's a horizontal between those cords, because we don't want that bending pressure of the span sets pushing in just towards on the top cords of the truss, potentially creating some issues there with bending. So we could get into a situation like this to where that happens. So we can see where they've got the pickup for the piece of truss is at a, and this is a European style truss with the conical connectors. So we've got a panel point on one side, but the span set on the other side is connected to an area where there isn't a panel point. We see localized bending between the panel points. So we want to make sure to avoid that situation. So truss that most people in North America are used to seeing, something like this. So I used to see this quite often, especially in roof systems where people were applying heavy PA wing loads to a piece of PRT. So they would load the PA wing, the PA right in the center of the PA wing. So you would have something similar to this happen, because PRT, the diagonals are different than what this piece of truss is right here, but you have the same effect. So always pay attention to the panel point. Always make sure that you have a wrap, or you have members above the wrap that are able to resist the forces. Anybody use wire rope or chain to lift truss? I hope not. You could have something like this. This is a PVC coated piece of wire rope. You can see that's it's done some damage to the truss as well.
Will, would you mind backing up
Yep.
backing up one photo?
I'm sorry.
Right.
This one?
I'm going to get asked, and I always do get asked by people say, well, I can't get into the panel point at the panel point. I need to go in between because that's where it's going to fit on my set, but I'm only hanging 50 pounds of something.
Mm-hmm.
Now, without using the two words that we're not supposed to use today, can I safely assume that there is a risk analysis that has to get done here to identify how far away you can get from a panel point with lightweight,
Sure.
decor kind of something. We're not talking about hanging a 10,000 pound line array here. We're talking about a 50-pound chandelier.
Sure.
So there's no prohibition on hanging in between panel points. The best place, of course, but you need to do your risk analysis to determine whether or not you're comfortable putting, that 50-pound chandelier in between an 18-inch gap in between panel points, in the middle of an 18-inch gap.
Yeah. what we used to tell, I don't know what we still do, what we tell customers, that if they're hanging a single point load, either on a horizontal, a bottom horizontal, or putting something between panel points, the maximum that load can be is 350 pounds.
Okay. That's a number.
Yep. That's an old Mike Wells developed number from back in the mid 90s.
Back in Mike Wells. Right. Okay. Well, hang that around his neck. Brian Martin has asked about using wire rope as a fire backup for slings on the hoist connection. Is that useful or not? You want to? Yeah, I mean, well, yeah, it's useful if it works, if you do it properly. But we've got other methods of hanging hoist now, where fire backups, a steel sling, is not necessary. It just makes the fire marshal happy.
Yeah, if they could do a piece of gack flex or something, that would be way better, I would imagine. Right. Bill, what else do you want to add to the whole slinging conversation here?
Well, I've got some imagery that I pulled off of the Facebook. We used to be riggers group, so we can go over there. There's a lot of, there's always been a lot of discussion and a lot of angst over the proper way to sling a truss, and Will and I've hamstrung Will and I a little bit, because we're not allowed to use those two words. But if you want to, Will, if you want to get out of this screen,
Yeah.
And I'll go to mine. Okay, so let's see. I am here, there. Okay, bear with me while I get my chat out of the way. So, and when you were, I was going to mention something when you were showing the slinging method for the double hung, the PRT.
Yeah.
And I guess I want to preface this by saying I have a default method of how I hang a truss. It's not the only right way to do it, but it's the way that I've adopted, so that anytime that I have to deviate from that default, it causes me to at least stop and think about it for a minute, right?
Sure.
And I think that's the part here that we have to pay attention to. There's a lot of ways to do it, but you have to think about it. If you're changing from a method that is tried and true, and you're going to another one because the circumstances require that, you want to stop, think about it, and make sure that what you're attempting is indeed appropriate. When I hang a truss, my default method is to choke on the outside of the bottom cord, do a wrap, again, coming up on the outside of the top cord. And yes, I wrap between the legs of the round sling, and then go up to the shackle and do the same thing on the other side. And I call that my default because I'm coming up on the outside, which gives me more stability because I'm a little further apart. And I wrap the top cord because in certain situations where I've got a 12-inch, that's on two hoists or with a 30-foot span, I want to control the top cord, the top of that truss, so that it doesn't start to roll when the LD puts a bunch of lighting instruments on one cord, on the upstage cord at center, and the whole truss now wants to start to roll, and I want to combat that. One of the things that'll happen that'll cause me to change that is if I've got a truss, the round slings that I've got for the truss aren't really the right length. And if I come up on the outside of the cords, I've got too short, my slings are too short, and they don't come up at this lovely little angle. They come, more horizontally across before I get to the shackle. Now I'm increasing the compression forces on the cords. I don't want to do that. So I give up a little stability and I choke on the inside, wrap on the inside and come up. I just picked up 2 inches on each side of sling length, so that now the compression forces aren't as challenging as they were before. And what, you know, this is the one that I picked up off of Facebook. Simon, are you still with us? I don't know if Simon is still with us or not. It's his Facebook group, and those of you who follow that group, they know the Dutch gentleman who's famous for putting these kind of things up in that group chat. But there are a bunch of ways of doing it. I don't know that there are any wrong ways in this chart. You may have to take your finger and kind of follow the load path a little bit on some of them to figure out exactly what's going on. But it seems to me that they all work and they all have, different circumstances.
There's a lot of creativity in there, that's for sure.
Say it again.
There's a lot of creativity in there, that's for sure.
There is indeed. I really like this one. I'm not quite sure if they're building a house or hanging a truss on that one. Let me swing over to the chat here and see what we've got. People talking about using wire rope slings as fire backups. In my experience, at least here in the States, the idea of using a steel sling as a backup has been replaced by using what used to be called a gack flex sling, but now it's called a steel flex sling. It's a round sling with that wire rope core, which satisfies fire marshals' concerns about burn through. So does anybody have any opinions about any of these? I have another one here I wanted to show you. And I'm not exactly sure what's going on here. I'm not sure if this is indeed a ladder truss laid on its side, or if they just chose not to show the bottom chord of a triangle truss. But regardless, I'm not exactly sure what's going on here.
Probably the thing isn't long enough to wrap both sides, but they want it not to slide when a load is applied.
What I hear you, and I think you're absolutely right. What I can't tell is whether I'm going to get an even distribution of force when I hang whatever I'm hanging underneath that truss, or whether it's going to want to try and roll it a bit. That's where I was having the difficulty. Robin has asked a question I think it's important to answer, and they want to know if there's a clear distinction in the difference in burn temperature between poly and gack. So a polyester round sling and a gack flex round sling. The polyester material suffers damage at 185 degrees Fahrenheit. And somebody help me out here. I don't remember what the melting point is for steel. Does anybody got that information? I don't remember, and I don't want to make it up.
It depends.
We have a winner, folks. Okay. Well, you know,
Google says 1425 for carbon steel.
okay.
Centigrade.
So-
Sorry, Canadian. 2600 to 2800 melting point.
Okay. So we go from 185 to 2600 in Fahrenheit.
But should we be worried about melting, or should we be worried about distempering or detempering?
Well, I'm not sure how much of a distinction we need to make. At 185 degrees, you know, that can happen really, really easily in a fire situation in a venue of some sort. And it could be localized and create a catastrophic failure. If you've got that much heat, or even approaching a 2,600 listen to me, 2,600 degree Fahrenheit temperature, I think you've got other issues going on than worrying about what the lighting truss is doing. If nothing else, the aluminum is going to start to melt at a significantly lower temperature than the steel. So I suspect you'll have dripping aluminum with a steel flex sling holding up bits and pieces. Michael has asked that he doesn't see ladder or triangle truss much anymore. Are they light duty trade booth type stuff, or can they be used on stage and in a stadium and weight put on it? Will, you want to talk about large triangle truss? Does it still exist? Do people want it?
We can certainly make it. You know, these types of odd trusses always seem to go through odd runs throughout different times of the year. So, you know, recently, about a month ago, we had a run of 12-inch ladder truss where we had 3, 4, 5 orders of people buying 12-inch ladder trusses. Like, this is weird. You know, we'll see that a lot of times with dance towers or just kind of odd things like that. Triangle truss, we don't see that very much anymore. We'll see people buying some 12-inch plated triangle for trade show type things, but the big truss, you don't see that much anymore.
Okay. I know that I used to have a metric crap load of 22-inch triangle truss. And,
wow.
You know, I had miles of the stuff. And when I bought my last batch of it, that was the last time I needed it. And
Right.
it sat in my shop for years till I finally scrapped it.
Aluma beer.
Aluma beer?
Yeah, Aluma
Yeah.
beer.
Oh, yeah, right. Anything else, folks? Other questions?
So, Bill,
Yeah.
yeah, we're talking about hanging the truss at the panel points, and how are we going to? So many times when we're hanging truss, and we've got limited resources in the overhead to hang the truss, and so often that we fall away from where the panel point will be in the truss. What advice have you got for us on that, Will?
A lot of it'll come down to what you're using as your connection device to the truss. So if you're using a span set, maybe you could bridge diagonally from one panel point to a, you know, if you're, I don't have a good way but like what Bill's showing there is if you were if you needed to move that panel point somewhere, maybe you could slide one side of that connection down to the next panel point, maybe, if you had to get somewhere in the middle. Like I said, there's some creative ways to try and get between panel points. There are also some pickup bars that are out there that you can rotate to a certain degree within the top or bottom of the truss. So you could rotate the couplers on them to get closer to a panel point and still get that connection, closer to a true hang.
One of the other things you can do, and this may not be an option very often, but if you've got different length truss sections in your inventory on site for that show, and maybe you're using, let's say, a 10-foot and a 6-foot piece of truss. Maybe you want to reverse the order, put the 10-foot on the other side,
Right.
or you need to make up 20 feet of truss. Get a 10 and 2 5s, something along those lines. Again, and Will, correct me if I'm wrong, please, but you got to look at I almost said it. You got to look and see what your load situation is. You have to do a risk analysis, and it doesn't mean I know that sounds terribly official, but it really can boil down to looking at it, maybe making sure the weight really is the weight that they think it is, making sure that the actual weight is accurate.
Yeah.
And maybe you have an opportunity to move it 6 inches down the cord and get that much closer to a panel point.
And you mentioned the sound too official or something like that, but we haven't dove into the ANSI standard for truss on this call, and we're certainly not going to have enough time to do that. But that's one of the user requirements in the ANSI code, is to make sure you've reviewed your load plot, make sure you have some type of a drawing of how the truss is being used, where the rigging points are, and things like that. That way you kind of know what you're getting into beforehand.
Yeah, it sounds terribly official, but you don't need charts and graphs and
Right.
photographs with 8x10 photographs with arrows and descriptions on the back, kind of a thing. Let's see how many people know that reference.
Alice's Restaurant.
Yes, it is. Thank you very much.
You're welcome.
But you stop and evaluate the situation. It doesn't even have to involve typing or writing. It just evaluate, look at it, and work it out in your head. Even it's not an official process necessarily.
In my case, it's a case of in a lot of the convention halls we have to hang in, we may do a rock show or some silly thing like that, and we're kind of really limited with the real estate we've got to hang from, and so often I find that I'm having to hang the thing right in the middle between the panel points. I've got no choice in the matter, so changing how I put the slings is an option, and I think from now on I'm going to certainly use that. Thank you.
Okay,
Yeah.
sure. We are over time, folks, so if you've got a bail, please do, but if you have no objections, we'll keep going. There's a couple of good questions in here. Kana has a bridle question mark. Kana, do you want to expand on that just a little bit?
It's actually me, Bill Simon, posing as Canna.
Oh, okay. I was going to say, your voice has changed.
It's all the dry heat, sand, too many camels. Just this point of not being able to get to a panel, using a 4-leg bridle either from the bottom cord to the top cords as a solution to getting the load nearer panels. That way you can incorporate 2 panels, or depending on the length of the bridle, a panel, miss one, and then another panel.
Yeah, that would be an excellent idea. I mean, obviously you have to have the height for that sort of thing, but if you've got the height, yeah, that'd be a great way to solve it.
And lengthen your bridle.
Dennis Booth asks, and this is for me, sorry, Will, but any difference in the top wrap for poly versus steel flex? And the answer is no. They both wrap the same way, and they both perform the same, or close enough to the same that I don't worry about it. And I've got to tell Scott England, that no, it's not that the rope table is still there, although it might be. It's just that the photograph is really, really old.
Oh, see, because I thought that was your new shop, but you know, I haven't been in the old shop in so many years. Like, could just faulty memory.
Yeah. Andrew is asking, truss pieces with odd number of diagonals can't mirror on both sides. Best practice? Question mark.
Yeah, that's really an issue with the 12-inch plated truss. You know, you'll see trusses that have that, depending on how it's being used in a grid or a span, sometimes you won't be able to keep those diagonals all flowing the way that you'd like to. My recommendation for that would be to try and move that odd piece of truss to an end somewhere, or to a corner block somewhere. That way it's not quite as noticeable.
Okay, but this I want to be clear that you're talking about it from a structural standpoint, not an aesthetic one, right?
Yeah. You know, I think mostly, actually, it's probably mostly from an aesthetic standpoint. You know, that way you just don't have the weird piece of truss out there where you have parallel diagonals in the middle of a span.
Right. Because we all know what'll happen after somebody sees that, right?
Right.
Scott asks, how does the brittleness of panel points affect the advantages of hanging at panel points?
The engineers have a heat affected zone reduction that they apply to the overall analysis of the truss. So the heat affected zone is already configured within the capacities of the truss.
Okay. Cool. Thank you. Torn asks, this is a good one. Really get you really good at the end here, Will. Do you have a recommended D rating for performer flying purposes?
Oh boy.
Yeah.
I'm not going to say it's a D rating, because performer flying is such a specialized art that's really becoming more and more popular within the entertainment industry. What the engineers will need to do, and they'll need to know what the stop reactions are of the equipment that the performer is using. So, you know, when we were dealing with Corteo, the last arena tour for Corteo, we spent days with the Tate guys down here in Knoxville with the engineers going over e-stop reactions. And, you know, if the carrier on the track was orientated, you know, a certain way, and all that e-stop was going into a single wheel on the track, you know, what does that track need to be able to resist? The performer flying is very complicated when it comes to that. And as Bill, you certainly know from the performer flying standard, with all the different types of reactions that those guys are dealing with, the engineering gets fairly complicated. So it's not a set, it's not a reduction, but we have to have somebody look at all the components together as the system operates.
So in layman terms, you're not going to take, say, you know, just for the sake of argument, you're not going to take a piece of 20.5 and reduce its capacity and let somebody fly someone on it. You'll find out what the load rating is going to be, what the worst case scenario is, and then you'll pick the truss to meet that, correct?
Correct. Correct.
Okay.
Bill, this is Tom. Can I jump in and rephrase the question then?
Sure.
So what I guess I was meaning was, do you add an extra, what I would call a factor of safety? So obviously, you know exactly what you're loading the truss with, then that's great. And obviously, performer flying, you really need to be careful about those dynamic loads. But I'm asking really, is I've been told by European manufacturers that they would double their factor of safety or half the allowable load, depending on how you want to put it. But you don't have that, take that stance?
No. The reason why we typically wouldn't take that stance is because when we've done those more high profile, and this is kind of getting away from, I think, where your question is on maybe the backyard aerialist that's trying to do something, but when we're doing those shows that are like Corteo or some of the automation that was in Marvel and stuff like that, we are testing the truss in its used configuration to full maximum zero stop capacity brake force. So we don't necessarily have to change. We're not adjusting the safety factor there because we're going through all that testing before we allow performers to hit the system. I think from a backyard aerialist standpoint, I think if the aerialist should have at least some type of a conversation with an engineer just to go over what type of acts they're doing. Is it a silk act? Is there some vertical movement that they're doing within the act as well? What the speed, weight of the performer, all that kind of stuff, and then they can try and figure out, okay, this is the right product to choose for your use.
If I can take that a step further, the number that everybody hears kicking around, and Andrew put it up in the chat, people always talk about having a 10-to-1 design factor, 10-to-1 factor of safety in a performer flying situation. And that's kind of let's call it the pedestrian way of doing it. It's just, you just throw 10-to-1 at the wall and it sticks, so you're good to go. In a lot of cases, there are other limiting factors, the room, the venue, the height, the ability to have a 4-foot tall truss or not. So you can start chipping away at that 10-to-1 design factor as long as you pick up the engineering side of it, so that you get closer to and actually do, as Will was describing, we actually know what the forces are going to be, because you test them and you test them and you test them and you test them. It's kind of like the fall arrest regulations here in the United States. When you're designing a system, you're using either the 5,000 pound tensile strength capacity, which is kind of the blanket statement, or if you identify maximum arresting force, you're allowed to design a system that's double the maximum arresting force. So there are other ways of doing it other than just snatching a design factor out of the air and applying that to it. There's nothing wrong with that, but there are going to be situations where you're not going to be able to do that and still be able to do your show. It's about 1/4 folks, and I'm not sure how many people we have left.
Yeah, 47.
47. Nobody went home. Cool. Cool. Well, keep the questions coming. I'm going to let this go till about, no later than 4, guys, because I do have other things I have to do today.
Bill, I've got a picture that I can put up real quick that would show the cam lock truss.
Oh yeah, I've already closed out, so you can take the screen.
All right. Can we see it?
Yeah, you can just barely see it over there on the left-hand side.
You can see that the connection plates are a little bit different than what you see on truss, on modern truss. You'll see that this is more ovaled, where the cam lock went through, and that's to account for that male T that would have to go through that. Then you can see these extra smaller holes on each side, and that was for bolting, because you physically have to bolt the cam lock connector to the truss itself.
Yeah, they were quick release devices, which is of course what you always want when you're putting truss together. You want something that's going to be quick release. This was Mike Wood, wasn't it?
What's that?
This was Mike Wood from Slick who came
No,
up with it?
that's a Tomcat Truss. That
I
was
know,
in
but
the-
didn't
Oh, yeah,
Mike,
I believe so. I believe so.
I'm showing my age here. I know, but yeah, when he first came out with it, everybody, looked at it. We went running, screaming from the room.
Those older models of truss, can you bolt that together still? You could still use.
Yes. Yeah, they can still accept a 5/8 inch bolt.
What were those slips for? What were those? I don't really understand what those slips were for.
So the cam lock, it was a male and a female cam lock, and the male had a stud on it with a T at the end that would go into a matching female, and it was a quarter turn lock. And when it went into that quarter turn lock, there were little nubs in the female that they would have to go over and to lock it in place. And that's what that tension screw set. The tension screw on the male side of the cam lock set the tension of what that crossbar was at, so it made it more difficult to go over those nubs inside the female. So if you had too much tension on it, you couldn't get that full quarter turn because you weren't able to get it over the nubs. So most people, after a few years of messing with these, they took all the cam locks off and they went back to bolts. But you still see, still see every once in a while a truss floating around that has these old cam locks on it, cam plates on it.
Andrew asked a question. It's a different subject, but Andrew asked, I think, a good question about anyone knowing a resource for load cell data on single silk or Lyra performers. Aerialist Act. Jonathan, are you still with us?
Yes, sir, I'm here. Yeah, there are a bunch of sources for lots of that data, and the fastest way of doing that is I'll put my email in the chat, and anybody can reach out to me for that. Is that all right, Bill?
Oh yeah, it's fine. Dennis is asking about the number of holes in the end plates for those cam locks. Different size truss, I assume.
Is he talking about the double holes on the medium duty?
Yeah, the one on in your photo.
Yeah. So this, you still see this in 20.5 inch truss. The cam plates still have dual holes in it. We always tell people to use the outer hole, but in some there are load tables that are out there that will give you a load bump if you want to use double bolts. So it does. I think it's about a 15 to 20% increase in capacity if you used all 8.
Copy that. Thank you.
Cool. Thank you. I didn't know that. Anybody else got questions? I think we've hit all the major ones in the chat, although I just saw one from Pamela about the rigging class in Texas. Tomcats no longer is in Knoxville. And the last class that they did this past February was in Rancho Cucamonga. Was it in no.
Thousand Oaks.
Yeah. Thousand Oaks, right. I was bouncing forth between those two towns while I was out there. Right. Is in Thousand Oaks, California, which is definitely not Midland, Texas.
Right. Yeah, the plan before COVID was now that we have the warehousing and offices out there on the west, was to bounce back and forth between east and west. So have it in California one year, then have it back in Knoxville, then kind of switch around. But now with COVID still floating around there, hopefully we'll be back to doing some type of Tomcat U again next year.
Yeah, I hope so. All right, folks. I think we've achieved nirvana here. Thank you all. Thank you, Will. Folks, Will gets paid real big money to do what he just did for us today. And I really do appreciate you taking the time and doing this.
Yeah,
doing
absolutely.
this for us, Will. This was fantastic.
If anybody has any questions, get a hold of me, call me, email, whatever. I like to talk sometimes.
Yeah, especially when you're only hanging around with your kids, right?
Exactly.
All right, all. Thank you very much. This video, the recording, will be up on the website, YouTube, sometime on Friday. Okay, and on Friday I will be sending out the announcement for registration for next week's class, which is Equity and Inclusion, Part 4. Thank you much, Will. Thank you again. I really appreciate it. Everybody, take care and stay safe.
Excellent.
Thank you, Bill.
Guys.
Thank you, Will.
Appreciate it.
Okay. Thank you all once again. I'm going to close up shop here, which, as you know, unceremoniously dumps you all out the door. Bye-bye.